So this is the answer of this. I have already shared this answer to the PPT. Okay, so all of you have seen the answer of this example. So I have not discussed this example. If you have any doubt, then you can ask me. Okay. So I move for the next topic: energy stored in the capacitor. So as you all know that the amount of energy stored in the capacitor, the purpose of the capacitor is to store the energy when it is not charged and provide the energy when it is fully charged. Okay. So amount of energy stored in the capacitor, that is 1/2 CV square. Okay. That you know the equation. So let's derive this equation of energy stored into the capacitor. So how the energy is stored in the capacitor? So first, initially your capacitor is uncharged. There is no charge in the plate of the capacitor. So to charge the capacitor, first apply the potential difference, or you can say the voltage applied across the capacitor. So when you apply the potential difference across the capacitor, the electrons are transferred from one plate to other through the source. The source is a voltage source, and capacitor is charged. So this process involves the expenditure of the energy because electrons are moved from one plate to another plate against the opposite forces. Opposite forces means your supply voltage. Clear? So this process involves the expenditure of the energy, and this energy is stored in the capacitor in the form of the electrostatic field, which is set up between the plates of the capacitor in the dielectric medium. So as you know that the dielectric medium or insulating material is placed between the two conducting plates. So this energy applied to this capacitor, that is stored in form of the electrostatic field, which is set up between the two plates in the dielectric medium. Now we can see the single line diagram of this process. So here you can see there is a source of energy, which is nothing but a battery, which has a volt V, capital V. And here is the capacitor. Upper plate assumed is a positive, lower plate is assumed is a negative. Now this is shown that your capacitor is charged at the same as your supply voltage. It means whatever the battery voltage, at the same voltage your capacitor is charged. Clear? Initially it is not charged, so there is no positive or negative polarity. All the plates are neutral. It means whatever amount of positive charge, same amount of the negative charge on each plate. Clear? So there is no charge, so there is no voltage. As you know the equation, charge is directly proportional to the voltage. So if voltage is 0 initially, then there is no charge across the capacitor. So consider that the capacitor of C Faraday, this is a C Faraday capacitor connected across the voltage source for the charging. Here is the voltage source for the charging. So during the charging, this work is done for shifting the charge from one plate to another plate. And suppose at any instant, this charge on the capacitor is Q coulomb and potential difference across the capacitor is V watt. It is a small V watt. Okay. Suppose at any instant of time before your capacitor is completely charged to this capital V volts, suppose assume that at any instant of time, the charge on the capacitor is suppose small q coulomb, and at that time the potential difference across the capacitor is V watt. So the value of capacitance is what? As you know the equation Q by V. So here small q, that is a charge on the plate of the capacitor, and divide by the voltage across the capacitor. So that gives a value of capacitance. So if you know the value of capacitance, so from this equation you can find out the amount of charge placed on the plate of the capacitor. Because once you made the capacitor, its capacitance is fixed. It means C is fixed. Clear? If you measure the voltage across the capacitor by using the voltmeter or multimeter, so by using this equation, Q is equal to C into V, you can find out the amount of charge placed on the plate of the capacitor. Clear? Now, if further is charged, so small amount of charge is shifted. So that small amount of charge we call as a dq. It means the change in the shifting of the charge from one plate to another plate. So charge is shifted dq. Then amount of work is required. That is, we write from this equation dw is equal to v into dq. Here. So W is what? That is the work done. V is nothing but voltage across the capacitor. And dq is the small change in the charge shifting from one plate to another plate. So this change in the work done, that is because of this change in the charge on the plate of the capacitor. And change in this charge, that is what? Because of the change in the voltage across the capacitor. So you can write the equation of dq as we write here in the, you know that q is equal to c into v. So if you differentiate this q, it means dq, c is always constant. So the equation dq becomes c into dv. So small change in the charge, that is because of small change in the voltage across the capacitor. So if you replace this dq is equal to c into dv in this equation of work done, so your work done, change in the work done, dw becomes c into dv, because dq is replaced by c into dv. So cv into dv, that is becomes the work done. That is for only small change in the charge, shifting from one plate to another plate. So for the whole process, from initial time where your capacitor is completely uncharged to completely charged, we want to find out the how much amount of work done is required during this process to completely charge the capacitor from 0 to V volt. So total work done in raising the potential of uncharged capacitor. For that, we make the integration of this equation. Integration of this dW is equal to CV into dV. So integration up to which point? So up to integration up to the capital V volt, because capital V is our supply voltage. You can see that in this figure, our battery voltage is capital V. So at the end of this completely charging, your capacitor voltage becomes same as your battery voltage. Clear? At any instant, we assume that it is small v. But when it is completely charged, it is becomes capital V, same as the supply voltage. So we take the integration from 0 to V. Why we take the 0? Because initially your capacitor voltage is 0. And finally, at the end of charging, your capacitor voltage becomes same as the supply voltage. So we take the integration from 0 to V, CV into dV. So that much amount of work done total is required to charge the capacitor fully from the 0 position. So you can see that if you take the integration of this, C is the constant. So take the integration of V into dV. So V into dV integration is what? V square by 2. Now this is a small v. Now replaced by this capital V, because at the end of the full charge, your capacitor voltage becomes capital V. So this small v is replaced by capital V. So your equation becomes 1/2 CV square. So 1/2 CV square, that is nothing but a amount of work done or amount of energy stored into this capacitor. Clear? So this is a derivation of the equation of amount of energy stored in the capacitor. So this stored energy into the capacitor you can write in a different way. So as you know that Q is equal to C into V. So you can also write this 1/2 CV square as a 1/2 QV, because CV is replaced by Q. Or you can write like this way. You know the voltage is what? Q by C. So in this equation, if you replace V is equal to Q by C, so equation becomes Q square divided by 2C. And we know that the energy unit is joule. So this energy stored into the capacitor, you can write by any of the equation 1/2 CV square or 1/2 QV, or you can write Q square by 2C. Unit of energy is joule. Okay. Now if you clear this topic, amount of energy stored into the capacitor, clear all of you? Is there any doubt in this derivation?
Yes, sir.
Okay. So let's calculate the examples related to this. Write down this example. Two capacitors having capacitance of 20 microfarad and 30 microfarad are connected in series across 600 volt DC supply. Calculate potential difference across each capacitor. If the third capacitor of unknown capacitance is now connected in parallel with 20 microfarad capacitor such that the potential difference across 30 microfarad capacitor is become 400 volt. Calculate the value of unknown capacitance and energy stored into the third capacitor. So write down this example and try to calculate this value of unknown capacitance, energy stored into the third capacitor, as well as calculate the potential difference across each capacitor. Yes, all of you get this answer? What is the value of potential difference across each capacitor? You can see this is the figure. Two capacitor 20 microfarad and 30 microfarad are connected in series across the 600 volt DC. Clear? This one. So first of all, find out this equivalent capacitance and then find out the amount of charge Q. And then you can find out the voltage across each capacitor.
Sir, unknown capacitance 40.
Yes, sorry.
Unknown capacitance value equals to 40 microfarad.
Yes, it is 40 microfarad. Yes. And what is the energy stored into the capacitor? Third capacitor means what? Unknown capacitor. See, second is asked that find out the energy stored into the third capacitor. It means the unknown capacitor which is connected in parallel with this 20 microfarad. Find out the energy stored in C3, this third capacitor. And give the answer what is the potential difference across each capacitor. First you find out this. Okay, potential difference across each capacitor. That is before connecting this third capacitor in parallel with this 20 microfarad.
Sir, across 20 microfarad potential difference is 360.
Yes, very good. Yes.
And across 30 it is 240.
Yes, very good. Yes. This is right. All of you get this answer? Voltage across 20 microfarad is 360 volt and voltage
Yes.
across C2 30 microfarad is 240 volt. Clear? And how much amount of energy stored into the third capacitor? It means third capacitor is the unknown capacitor, which you calculate, you get the answer 40 microfarad. Okay. So how much amount of energy stored into the third capacitor?
0.8 joule.
0.8 joule. Yes, it is the right answer. 0.8 joule. Yes. So those who have not get the answer, let's understand here. So first you calculate the equivalent capacitance when two capacitor 20 and 30 microfarad are connected in series. So C equivalent becomes C1. Here there is a printing mistake. It is C1 multiply C2. So C1 is 20, C2 is 30. So 20 multiply 30 divided by addition of these two. C1 plus C2. So you get the equivalent capacitance is 12 microfarad. Then after finding C equivalent, find out the amount of charge. Because two are connected in series, so same amount of charge is passing through these two capacitors. Clear? So Q is equal to C equivalent into V. C equivalent is what? 12 microfarad, and voltage is supply voltage 600 volt. So amount of charge passing through both the capacitors C1 and C2 is 7200 microcoulomb. Clear? Now, as you know the equation of voltage, V is equal to Q by C. So first of all, find out the voltage across C1. So voltage across C1 we call VC1. So it is Q divided by C1. Q is constant in both the capacitors. It is same. It is 7200 microfarad divided by C1. C1 is 20 microfarad. So you get the answer 360 volt across the 20 microfarad capacitor. Same way voltage across C2, 30 microfarad. Charge is remain same, 7200 microcoulomb divided by 30 microfarad. So you get the answer 240 watt. So that is the first answer. Calculate the potential difference across each capacitor. Clear all of you up to this? Now next, find out the value of unknown capacitance. So here third capacitor that is connected in parallel with the 20 microfarad, which is a C1. So C3 unknown capacitor that is connected across the C1. So at that time, what is the voltage across the C2? Voltage across the 30 microfarad, that becomes 400 volt, and supply voltage is 600 volt here. So because here you can see that initially the voltage across C2 that is only 240 watt, but after connecting this C3 across C1, the voltage across C2 that increased from 240 to 400 volt. So it means that this voltage increase, it means the amount of charge passing through this C2 that is increasing. Clear? Because C2 is constant, so voltage increase only and only if the charge passing through the capacitor is increased. It means find out the new charge which is passing through the C2. So as you know, the equation of Q is equal to C2 into VC2. VC2 is the voltage across C2, which is now become 400 volt. So C2 is 30, VC2 is 400. So now the amount of charge passing from this C2 30 microfarad is 12,000 microcoulomb. Initially it is passing 7,200. Clear? But by connecting this C3 across C1, now charge is passing is 12,000 microcoulomb. And C1 and C3 connected in parallel, so equivalent is addition, C1 plus C3. C1 is 20, C3 is unknown. So as you know, the voltage across C2 is 400, supply is 600. So amount of voltage across C1 and C3 becomes automatically 200. 600 minus 400. Clear? So now from this equivalent capacitance 20 plus C3, you can derive the equation of C3. Derive the value of C3. So 20 plus C3 equivalent capacitance is equal to what? Q by V. Q is what? 12,000 microcoulomb, and divide by volt. Voltage across this C equivalent is how much? 200. Divide by 200. So finally you get the answer 40 microfarad. I hope you understand that how to get the answer of unknown capacitance. Clear up to this? So that is the second answer. And third one is energy stored into this third capacitor. It means this 40 microfarad. So simple equation 1/2 CV square. So C is 40 microfarad, V is voltage across this unknown capacitor 400 volt. So you get the answer 0.8 joule. Yes, is there any doubt? Anyone in this example? Yes, anyone? Anyone, any doubt? Yes or no?
No, sir.
Okay. So next topic is charging and discharging of the capacitor. So before going to discuss this topic, all of you plus first see this video related to the charging and discharging of the capacitor. All of you can see the screen, VLC file. બધાને દેખાય છે?
Yes, sir.
Yes, sir.
Oh, okay.
Sir.
So, okay, let's listen this video, and then after we move for the topic charging and discharging of the capacitor. First see this animation video.
Sir, we can't hear audio.
Yes,
We can't hear audio.
ઓડિયો નથી આવતો તમને?
Nah, sir.
Okay, 1 minute.
Sir, and the video is also stuttering.
Okay. 1 minute. Now you can hear this voice. આવે છે બધાને અવાજ?
Sir, you have paused the video.
Yes.
No, sir.
No.
Let's see it again.
Sir, still voice is not coming.
No, sir.
નથી આવતો અવાજ?
Nah.
Hello.
No, sir.
Okay,
So
no
you
problem.
need to stop sharing screen and then again share. While sharing screen, you have to enable the system sounds.
Okay,
Then,
okay.
then only it will be audible.
Okay. Now you can see this video screen. Screen દેખાય છે બધાને?
Ha, sir.
Oh, okay.
Yes, sir. આવે છે અવાજ બધાને?
No, sir.
No, sir.
No, sir.
1 minute. આવે છે અવાજ બધાને?
Sir.
No, sir.
Yes or no?
No.
સ્ક્રીન દેખાય છે બધાને વિડીયોની?
Yes, sir. Screen is visible.
Okay. So I will share this video. Okay. Then you will see this video. Then after we'll discuss it on the next lecture. Okay. So let's start the theory first. I will give you the link of this video. You can see it. Okay. No problem. Now you can see this presentation. All of you?
No, sir.
No, sir.
No,
Nothing
sir.
देखा तू?
Nah.
1 minute. Now, can see this?
Yes.
Yes.
Yes, sir.
Okay.
Yes,
Okay.
sir.
Okay. So let's start the new topic: charging of the capacitor and discharging of the capacitor. So let's understand this by taking this figure as a reference. So here you can see that supply voltage Vs. You can assume this is a battery. In series with resistance and capacitor are connected in series. In series we connect the switch. Now initially it is open. Assume that initially this capacitor is uncharged. Means there is no charge on the plate of this capacitor. Clear? And when you close this switch, after this closing the switch, your capacitor will start charging through the supply voltage. Clear? So how the charging happens on the capacitor? So let's understand this from this figure. So this figure has a capacitance C, which is connected in series with the non-inductive resistance R, and combination that is connected to the DC supply V1. So it is a DC supply Vs is connected to this RC through this switch. So for charging of this capacitor, we must close this switch. And at the instant of closing this switch, what will happen? Your current will start flowing. But initially there is no charge on the plate of the capacitor. Clear? It means your capacitor is initially discharged. So once you close this switch, current is start flowing from this supply to this resistance and capacitor starts charging. So initially there is no charge across the capacitor. It means that there is no voltage across the capacitor. Here, so as you know the equation of Q is what? C into V. Clear? So if Q is 0, there is no charge on the capacitor, so voltage is also 0. So initially voltage V subscript CT, that is 0 because initially your capacitor is uncharged. So initially Vc is 0. Once closing the switch, capacitor will start charging. Yeah. So as a result, when you apply the voltage and switch is closed, the whole supply voltage that momentarily come across the resistor. Why across the resistor? Because you can see that in this figure, initially voltage across capacitor is 0. So voltage across capacitor 0 means what? It is act as a closed path, or at least act as a short circuit. Clear? So initially your whole supply voltage Vs that directly come across this R. That is only for the small period of time. This is a momentary action. But once your capacitor is charged, the voltage across the capacitor is also increasing because charge will increase. Clear? As the Q is increases, voltage across capacitor is also increasing. But initially momentary, when you close the switch, at that time, supply voltage come across this resistance. Initial time. So as a result, the initial value of charging current becomes equal to V by R, and which is maximum possible. Because in your circuit, initially there is no voltage across the capacitor, there is no resistance offered by the capacitor. So current flowing through this circuit is supply voltage divided by resistance only. And this is the maximum amount of possible current flowing into this circuit. So charging current is gradually decreases from its maximum value. Maximum value is V by R. Clear? So once you close the switch S, initially maximum current is flowing Im, that is V by R. And as the time passes, this maximum current value is decreasing. It means this charging current value is decreasing. So the charging current gradually decreases from its maximum value till it is finally becomes 0 when the potential difference across the capacitor plates becomes equal and opposite to the supply voltage. It means what? Here in this figure, initially Vc is 0, but once your capacitor starts charging and becomes fully charged means voltage across capacitor becomes same as the supply voltage. Yes. So what will happen? This positive voltage of supply with the magnitude Vs, same upper plate of this capacitor with the positive magnitude, and the same voltage Vs So it means that there is no potential difference between source and this capacitor. So what will happen when there is no potential difference? Then no current flowing into the circuit. It means I becomes 0. Clear? Initially current I is maximum. It is V by I because initially capacitor is uncharged. Vc is 0. But once it is charging and becomes fully charged, after end of the charging time constant, your voltage across capacitor becomes same as the supply voltage. So there is no potential difference between supply and voltage across the capacitor. So there is no current flowing into this circuit. Clear? And at that time, the voltage across the capacitor, we can say that same as the supply voltage, and current becomes 0 to the circuit. So after closing the switch, capacitor starts charging and voltage across it increasing gradually up to the same as the supply voltage. And once it is become supply voltage, the charging process of the capacitor is over. It means we can say that your capacitor is fully charged. Clear? So let's understand this process by mathematically. So let's assume that an instant during the charging, the voltage across the capacitor is small Vc. Potential difference across the capacitor is small Vc. Okay, not capital Vs. It is small Vc. Now I is the charging current. Q is the charge on the plate of the capacitor. So according to the Kirchhoff's second law is KVL. Okay, so Kirchhoff's second law, applied voltage is equal to what? Voltage drop across the element. So here applied voltage is what? In this figure, Vs, supply voltage. Now voltage drop across R and voltage across capacitor. So Vs is equal to voltage across R and voltage across capacitor. So that becomes your KVL, second law of Kirchhoff. So applied voltage is equal to potential difference across R plus potential difference across C. So supply voltage is V, voltage across R is IR, and voltage across capacitor is small vc. That is at any instant of time during the charging. Okay. So as you know that the equation of current I is equal to what? Rate of change of charge with respect to time. You can write dq by dt. So q is what? C into vc. Vc is the voltage across capacitor. C is the capacitance of capacitor. C is constant. So I is equal to C into dvc divided by dt. Here C is a subscript. Okay. It is not a multiplication of capacitor. It is V subscript C, voltage across capacitor. So replace this I, replace the value of I, C dvc by dt here in this equation, number 1. So that becomes C dvc by dt into R plus voltage across the capacitor. So now this equation, take this Vc in this right hand side, left hand side. So become V minus Vc is equal to Rc into dvc by dt. Here, this Vc comes this side. So V minus Vc is equal to Rc into dv subscript c by dt. So dvc, this one, divided by V minus Vc, that comes here in the denominator. Dt comes here in the numerator and Rc comes here this side. So that becomes dt divided by Rc. Okay. Here there is a printing mistake. It is not a minus Rc. It is a plus Rc. Okay. So dvc by V minus Vc is equal to dt by Rc. Now take the integration of this equation. So by multiplying a negative side both the sides, right hand side and left hand side, and then after taking the integration both the sides, so you get the answer log V minus Vc. Integration of this dvc by V minus Vc is log V minus Vc, and integration of minus 1 upon Rc into dt, that is minus T divided by Rc plus K. We name this equation number 2. Now K is what? That is the integration constant. So how to derive this integration constant? So that is by using the initial condition. So as we know that during the charging, initially your capacitor is not charged. It means voltage across capacitor is 0. It means V subscript C, that is 0 at T is equal to 0. So initially E is equal to 0 time, Vc is 0. So put this value T is equal to 0 and Vc is equal to 0 in this equation number 2. So you can find out the value of K. So Vc is 0. So here this left hand side becomes log V. T is 0. So this term is 0. So it means K is equal to what? Log V. Clear? So put this value of K log V in the equation number 2. The remaining equation is as it is. Log V minus Vc is equal to minus T upon Rc plus log V. Clear? So that is look like this way by substituting the value of K in the equation number 2. So when this log V come to this left hand side, so that becomes division of log V minus Vc divided by V is equal to minus T upon Rc. Okay? So if you remove this log by taking the anti-log, so you get the V minus Vc divided by V is equal to e raised to minus T upon Rc. Here, if you remove here log, so here this side becomes e raised to minus T upon Rc. So V minus Vc is equal to what? This V is multiplied here is e raised to minus T upon Rc. So it is V minus Vc is equal to V into e raised to minus T upon Rc. So voltage across capacitor Vc, that becomes what? V into 1 minus e raised to minus T upon Rc. By taking the common V, so finally the equation of voltage across the capacitor, that becomes V into 1 minus e raised to minus T upon Rc. Rc is what? That is nothing but a charging time constant that we call as a lambda. So lambda charging time constant, that is equal to Rc. So if you draw the graph of this voltage across the capacitor with respect to time, so it is look like this way. So as you can see that at T is equal to 0, here the voltage across the capacitor is what? 0, because T is equal to 0 time, capacitor is uncharged, so you get the 0 voltage. But as the time passes, as the time T is increases, you can see in this equation, as this T is increasing, what will happen? This second term is decreases. It means that your voltage across the capacitor that reach toward this supply voltage. It means V. V is the supply voltage of the battery. So you can see that it is gradually increases as the time passes. And after the charging time constant, that becomes equal to V. Clear? So when it is fully charged, your Vc, that becomes V. Clear? So that is a graphical representation of this equation. Vc is equal to V into 1 minus e raised to minus T upon Rc. Clear all of you? This derivation of charging of the capacitor, derivation of voltage across the capacitor during charging. Is there any doubt in this derivation? Yes, anyone?
No, sir.
Okay, okay. So let's move for the example related to this charging process of the capacitor. So write down this example. A capacitor of 8 microfarad connected to a DC supply through a resistance of 1 mega ohm. Calculate the time taken for the capacitor to reach 95% of its final charge. So here you need to find out the value, find out the value of time required by this capacitor to charge 90% of its final value. Here we assume that the supply voltage is V. So you can use this equation, this one, voltage across the capacitor, to derive the value of this time T. Okay? So R is given 1 mega ohm, or you can see the 10 raised to 6 ohm. Capacitor is given 8 microfarad. Now your VC capacitor.
Sir, can you go back to the last slide?
Which this derivation?
This is the question.
Okay, sorry.
Okay, sir. So you can change the slides now.
Okay, we try to calculate this time taken by this capacitor to reach the 95%. Okay, so I give you the hint. So here, which time you calculate? So time is required by this capacitor to reach 95% of its final value. Final value means same as the supply voltage. So here supply voltage is not given. So assume that the supply voltage is V, capital V. So your VC is reached the 95% of supply voltage. It means that VC is equal to what? 0.95 into V. Clear? And here R and C is given. So R is the 1 mega ohm, C is 8 microfarad. So you get the lambda charging time constant is 8. You can see here in this derivation. And put this value of charging time constant in the equation of voltage across the capacitor. This one, VC is equal to V into 1 minus e raised to minus T upon RC. Here RC is what? Charging time constant, lambda. Clear? So that we have calculated here, lambda is 8. So use this equation. You can also call as a T. Okay. We also call as a T, charging time constant. We also call as a capital T, or you can also call as a lambda. You can write anything. Okay. So here VC is equal to V into 1 minus e raised to minus T upon T or lambda. So here VC is what? It is 95% of supply voltage. It means 0.95 into V. Here. So replace this VC by 0.95 into V. And here in this equation, there is a V at the right hand side. So this V cancel out. So left hand side becomes only 0.95 and right hand side is 1 minus e raised to minus small t upon capital T. Okay? So this becomes e raised to minus t upon t is equal to 0.05. Okay. Here it is a printing mistake. It is a e raised to minus t upon t. Okay. Not plus t upon t. So correct this error here and write down e raised to minus t upon t is equal to 0.05. So e raised to t upon t is what? That becomes 20. It means inverse of this 0.05. This one is e raised to minus t upon t, that is 0.05. So e raised to t upon t, positive e raised to t upon t, that becomes 20, inverse of 0.05. So t by t, by taking anti-log, so t by t becomes what? ln 20. So ln 20 is what? 2.99. So your t charging time, that becomes 2.99 times this capital T, charging time constant, that we already calculate, which is 8. So 2.99 into 8, that gives a time required by this capacitor to charge up to the 95% of its final value. So answer is 23.96 seconds. All of you understand this example? Can I repeat again? Or can I repeat again? Is there any doubt?
No, sir.
Okay, so please write down this example.
Excuse me, sir.
Yes.
Excuse me, sir.
Yes,
So
yes. please.
that e raised to t upon t is equal to 20. So that how is it there? Can you explain once?
What? How you get this
E
e raised to
raised
t
to
upon
t upon t. Yes, sir. Yes, sir.
Yes. Yeah, this is a e raised to minus t upon t. Here, this e raised to minus t upon t, that is equal to 0.05. This is a printing mistake here. It is a minus t upon t. Okay.
Okay.
So if you take the inverse of this, so it becomes positive e raised to plus t upon t. So you require the inverse here at the right hand side also. So inverse of 0.05 is what? 1 upon 0.05, that is 20. Clear? So that's
Okay,
why
okay.
it becomes e raised to t upon t is 20. Clear? Convert positive to negative.
Yes.
Taking the inverse.
Okay, sir.
So now is there any doubt? All of you place correct here. It is a e raised to minus t upon t is equal to 0.05. Okay. Because that creates the confusion here. So can I move for the next example?
Yes, sir.
Okay. So next example, a capacitor of 50 microfarad connected through 100 kilo ohm resistance to 230 watt DC supply. Calculate the time taken to reach the capacitor voltage to 200 watt after the closure of the switch. So it is similar to the previous example. Use the same equation, Vc is equal to V into 1 minus e raised to t upon lambda. Here supply voltage is given, capacitance is given, resistance value is given. So find out the value of time taken by this capacitor to reach 200 watt. Here. So I give you this example for your homework. Give me the answer in the next lecture. So here I stop this lecture. If you have any doubt, you can ask me now. First, write down this example. I give you the answer. The answer of this example is T is equal to 16.65 seconds. Okay. So here I stop this lecture. Okay, all of you.
Yes, sir.